started.
Okay, we are live.
Hello all. A very warm welcome to the third session of webinars which are delivered by our eminent speakers thriving in their respective fields of geosciences. Seneca has famously stated that desultory reading is delightful, but to be beneficial, our reading must be carefully directed. And today, I call specifically a very warm welcome to the third session. Professor John Dunan Winter has directed mostly all the geologists in the inception of their careers through his guided texts and books. I will now request our distinguished faculty, Professor Prabhakar Naraga, to introduce our esteemed guest speaker. Over to you, sir.
Yeah, dear participants, students, and my colleagues, welcome to the webinar 3 of PROTOLITH 2020. I'm honored to introduce Professor J.D. Winter, Faculty of Geology, Whitman College, Washington. The Professor Winter is a renowned American geologist who specializes in metamorphic petrology, mineralogy, crystallography, and geochemistry. As we all know that the Professor Winter doesn't need an introduction, and we are all aware of his familiar book on principles of igneous and metamorphic petrology, which laid the foundation of advanced knowledge for many of the budding geologists. And this textbook is one of the benchmark contribution of Professor Winter, and we still use it as one of the reference book for most of the understanding the processes of igneous and metamorphic rocks. And Professor Winter received his undergraduate degree in geology at the University of Illinois and completed his master's and PhD from the University of Washington, USA. Professor Winter studied several processes that took place during the formation and subsequent development of the ancient deep continental crust, and also worked on several processes related to the contact metamorphism. And he also worked as an exploration geologist in several areas of the dunya. And with this brief introduction, it's our immense pleasure to have Professor Winter to deliver a talk on magma chambers and magma diversity. And welcome, Professor Winter, to the talk.
Thank you very much. I appreciate the introduction. Thank you.
Thank you. Welcome.
I have always been a generalist, and I kind of enjoy the big, broad brush sort of ideas, which is probably why I wrote a textbook in the first place. Incidentally, I am now hopefully nearing halfway through a third edition, so I'm revising the book, and it'll be a lot cheaper the next time around, I'm hoping too, so you might be seeing an entirely new book. And I'd like to sort of talk about some of the things in one of my chapters about magma diversity that has sort of changed a lot recently, and I found it pretty interesting. So I thought I'd just take you through a little walk. There'll be some overlap with what I'm talking about, along with what Professor Rawlinson will be talking about shortly about formation of the continental crust, but not much. It's going to be some overlap, but some different things. So let me just go through a few basics. I'm sure most of you, if not all of you, are quite familiar with this stuff, but it does frame the question, okay? So you all know that the Earth is divided into mantle, core, and crust. And the composition of the mantle is, from everything we can tell by seismics and samples that make it to us, it's an ultramafic. It's a 4-phase laterite with an aluminous phase in addition to pyroxenes and olivines. Composition of the continental crust, well, you in India probably know quite well, since you see some pretty deep sections into it. If I were to take a heroic average of the continental crust, usually it's said to be granitic. It's more likely somewhere between an average andesite and a dacite. And then the question is, when and how did the continental crust form? This is what I'm pretty sure Dr. Rawlinson will be talking about shortly. But what I can say right now is that this continental crust did not form all at once during the Hadean to Archean episode in which the silicate earth separated from the core. That was a pretty dramatic event during the very early stages of the planet's development. But the continental crust did not form as sort of a second silicate scum on the top, at least not very much of it. The continental crust has been forming slowly and accumulating for some long time. Okay, so given those very basic sort of thoughts, let's move on to how you get granitic crust from a lertzolytic mantle. Again, you might be familiar with this phase diagram, which shows the mantle here, and these are some metamorphic reactions in which the aluminous phase at shallow depths is plagioclase, going to spinel, then to garnet, and then a lot more exotic things as you get deeper. Things like ringwoodite and periclase and things like that, perovskite. So, one thing we can say pretty clearly, the average geotherm is down here in solid lertzolite. In other words, under normal conditions, the mantle does not melt. So we have a solid mantle, and you can tell this because S seismic waves propagate all the way through it, and they would be stopped if there were some naturally igneous layer. There's several ways to get a partial melt, but I'm going to stick with a standby that's been very reliable for things like under mid-ocean ridges or in plumes, and that is that instead of rising mantle uplift, like let's say you get some rifting taking place and the mantle rises up to fill that, if it does it extremely slowly, the mantle would follow the geotherm. It would cool as it rose, okay? But rocks are notoriously poor thermal conductors. But since I like rocks, I like to think about that, as extremely good insulators. How's that? So these mantle materials will rise along an adiabat, which is a constant heat, not losing heat to the surroundings. So they'll follow a trajectory more like this instead of the geotherm, at which point they will intersect the solidus and begin to melt. At that point, the rising mantle will take a slightly different lower temperature curve because it is now losing heat as the latent heat of melting. And you can see that you can cross 15, maybe even 30% melting by the time you reach the surface. So this is step one on making granites, I suppose, okay? What is it you do make at this point is, okay, what is going to be the composition of that, let's call it a typical partial mantle melt? Well, there's a lot of ways to approach this thing. You can look at the amount of melting required before you can extract the melt. There's some threshold porosity. Then you can look at the buoyancy of the melts produced once it's reached that porosity and the interconnectedness of that. I mentioned dihedral angle here. That is the angle of, these are the crystals here in white, and these are melts starting to form at triple junctions between crystals. The dihedral angle is this angle right here, which is also this angle here and this angle here. So small dihedral angles will cause the liquids to wet the surface better than really large dihedral angles in which the liquids will get stuck. So here's small dihedral angle, large dihedral angle. Here's small dihedral angle creating an interconnected network. Once that gets interconnected, as in this kind of a diagram, buoyancy takes over and the melts can rise and get removed from the solid behind. Other ways to approach the typical mantle composition or melt composition is to model the melting using bulk standard earth as a composition for the original mantle, and then you would have your distribution coefficients and make assumptions on whether the melting is done by batch melting, fractional melting, etc., and you can kind of calculate what would result in a melting model. You could also use canned melting software like the MELTS program of Mark Yorso. And then all you have to do is plug in assumed values of F, the amount of melt produced, depth of melting, oxygen fugacity, whether you want batch or fractional, and see what you get. Perhaps better yet, and more reliable for decades, is take a sample of your laterite from a kimberlite or a nodule and start to melt it experimentally and see what you get. Or you can take a survey of what we consider primary melt compositions. All of those things lead basically to an analysis like this, which is a tholeiitic basalt. Okay, so this is probably what you're going to produce that is extractable from the mantle residuum and would make it up into the crust. So there's what you've got to start with, your first melt. Then what's the composition of a typical granite? Well, here's an I-type, an S-type, and an A-type granite analysis to compare to our basalt. All you have to do is go from here to here. And how might you then go about doing that is going to be a question, right? How do you create a granite or rhyolite from a parent basalt? So, if you just ask this on a simple mass balance, you could look at, I've highlighted K2O here, all right? K2O is about 0.5% in our basalt, but it's, I don't know, let's call it 4% in a granite. How much would you have to remove from a basalt in order to create a granite if you just thought about this most incompatible element? Well, you'd have to go by 8 times to go from 0.5% to 4%. That means you'd have to remove 7/8 of the other stuff to concentrate that 1/8 left into granite. So basically, you'd look at around 90% fractionation as a bare minimum, and that's assuming that your bulk partition coefficient was 0. In other words, all of the K2O stayed in the melt and none went into early solids. That would require 87.5% crystallization. Okay. So by fractional crystallization, you can do this. There is, of course, a problem. This is Yosemite Valley in the Sierra Nevadas of the western United States and California. Everything you see there is granite. Okay. So if this is going to be the last 10% of crystallization from our parent basalts, one has to ask where the heck all the rest of the other 80, 90% happens to have gone. When I started out in geology back in the 60s, that was all conveniently just told it's sunk somewhere, it's underground. It's the original method of geology sweeping a problem under the rug. And if you look at old intro texts, you see these granite batholith plutons sitting here underneath the carapace of sediments, but they just seem to get larger as you go down, saying that they somehow have an infinite size. This clearly is a problem if you're going to try to be able to create this stuff instead of just imagine it somewhere down there. So let's just quickly review some of the ideas about magmatic differentiation. We're going to start with our basalt, and we want to make a granite. So, number one in everybody's book, ever since the days of Norman Bowen, was that crystal fractionation is the be-all and end-all. Crystals form in your melt, and then due to gravity, they settle on the bottom, and the residual liquid then becomes the liquid of interest. This has been modeled on Stokes' law, which I put in here for you. That's the velocity of settling, that's the gravitational constant, that's the radius or the size of your crystals. These are the densities of your solid versus your liquid, the density contrast, and N is the viscosity. Notice it's times 9. So viscosity plays a pretty big role. Okay? Well, there's 2 questions to really address when we talk about magmatic differentiation. One is just, how do magmas differentiate? And so this is a really good method. It's responsible for a lot of it. The other question I'm trying to answer is, how do you make granites, especially all of that granite? And that's going to be a lot more problematic. Okay. So historically, crystal settling was at one time the be-all and end-all of magmatic differentiation. if you start to plug in some numbers into Stokes' law, you'll find out that olivine in a basalt will probably sink around a meter a day, which is not bad. A feldsparred rhyolite is going to be more like a meter per year, at least under the very basic assumptions. So it's a great way to evolve basaltic liquids, and there's a number of cases in the field where you can demonstrate this is so. But making a granite is going to be tough. Okay? Plus, there's the whole issue of non-Newtonian behavior, in which liquids have a yield strength instead of just a viscosity. And that yield strength builds up considerably as you go from basalts into more evolved liquids. There are very compelling arguments that once you get more than 40 to 50% crystalline, the system locks up. It becomes challenging to separate crystals and liquid beyond that point. It's a combination of high viscosities as the melts get more silica rich, and also these crystals start to form a network of mutually touching crystals suspended, which then don't seem to allow. It's all very nice to look at this pile down here, but you notice they're overlapping each other. They're usually not going to. There's going to be interstitial liquid here. So usually 40, maybe 50% is considered the sort of lockup amount. And of course, this is the basis for the argument I just made before, that the remaining 10% has to be granite. It's impossible, in my opinion, to get there doing crystal settling. Volatile transport is another method. That's the release of water or CO2 or some other volatile due to decompression. So you take the pressure off, the volatiles escape, and crystallization and cooling. Volatile transport is not going to be particularly effective either. It's been fairly popular for the origin of pegmatites, but even that is now being questioned. It also faces the identical mass balance challenges that crystal fractionation does. Volatile transport will take some materials out of melt, but there can't be enough to create the kind of granitic or rhyolitic nimbrites that we see today. Liquid admissibility was at one time looked forward to as a method by which granites could just exsolve out of a liquid. The original liquid admissibility was this narrow one here in the phaolite silica region here, the binary. It was first noticed in experiments, and later it was seen in samples, particularly in some lunar samples. But then we found that there was a larger admissibility gap as one heads out toward lucite, or in this case you can see it in orthoclase. So we're starting to sound a little more granite-like. So there is a fairly large two-liquid solvus right here. Turns out these two solvi are the same one. You can see the solvus in 3 dimensions here. This one here is this one here, and this one here, of course, is this one here. So this is just where the liquidous surface is intersected by this two-liquid solvent. Hope that's you can visualize that. And here's a little example of a liquid of bulk composition X that is crystallizing phaolite. If you remember playing with this in my chapters on crystallization of phase diagrams, and my liquid will then move directly away from the bulk from phaolite until it intersects the two-liquid solvus, and then this liquid will coexist with the liquid over here, and as you continue to cool, this liquid goes to here, and this liquid goes to here, and as soon as these three become collinear, that means this liquid is consumed, and this is the only remaining liquid, and then by continuing to form phaolite, your new liquid will move over here. This liquid is going to be quite a bit more granitic than this liquid. So there was the hope that this might be able to produce it, but I think you can realize that you're not going to be able to have very much of this liquid by the time you get here, and this liquid is already pretty evolved as you come through the rest of the system and hit this. In other words, you're not going to form the Sierra Nevadas this way. Here's a photomicrograph, by the way, of it's 10 micrometers here. This is a glass of a more basaltic liquid of composition like so, and these are glasses of closer to rhyolitic composition over here. So you can form them. But notice, they're virtually trapped in this matrix of mesostasis and crystals, and these things did not escape. And you can imagine how many of these you'd have to add together to create the continental crust and granite. Magma mixing was also a very popular idea for a while. If you look at a lot of areas that have a range of igneous rocks in them, bimodality is common. In other words, you usually see more mafic rocks, basic rocks, and you see more silicic rocks together. You rarely see what you might expect if crystal fractionation were dominant, which you'd see progressively less and less mafic, and then a little bit of residual granitics that manage to make it that far down the line. Instead, we tend to see a lot of bryolites and granites, and we see a lot of basalts, but fewer of the rocks in between. So the early thought here was that basalt and granite were the two principal primary magmas, and therefore you just mix them together to form the few rocks that you saw in between. This idea, which is definitely pre-plate tectonics, and before we knew a lot about what constitutes the continental crust and all these granites, sorry, tapping my mouse makes it jump. There's just no reasonable way that you can create granite from basalt. You have to start with a 2, and a granite is just simply not a primary magma except for maybe a little bit of scum that was formed in the Hadean, but it's not going to answer our problem of creating basalt. I'm going to return to magma mixing in a moment, though, because it is getting a resurgence, but not in the way we're thinking. Assimilation, in which a magma assimilates by heat some of the country rocks it passes through, is another way that you could pick up a granitic component, but like mixing it assumes that that granitic component is already there. It's not going to help you create that from your basalt. Okay, so there's a number of in situ processes we can think about, but I'm rather partial to just this one because it's simple, like I am. If you have a chamber here that is basically, let's call it a basalt, and you're going to have a temperature gradient toward the walls, and that means that this lower temperature rock will be it'll be entirely crystalline. This will be the solidus boundary right here, where it's cooled against the wall rock. And this in here would be somewhere near the liquidus, where you're too hot to form any crystals. So you get a full gradation from the liquidus to the solidus, and as a result, you get a full gradation in magma compositions from near basalt all the way up to pretty highly evolved in here, because so many of these crystals have already formed from these melts in here. Now, again, you do still have some of the problems of how to extract those melts, but notice that their buoyancy as they work up here is a lot better, so that they can move out across the roof. Wes Hildreth proposed this for the Bishop Tuff, a rhyolite tuff, and there's a lot to be said for it, but there's also a lot of questions about how you actually move this liquid. Also, I've talked about a lot of these ways to do things. There's a bunch of combined numerical models that are becoming more and more prevalent, particularly with computing power. AFC, oops, sorry. bouncing my mouth. AFC is assimilation, fractional crystallization. Some of the heat of crystallization, the latent heat of fusion is used to help assimilate. There's an AIFC, I'm partial to anything imperfect, and that's imperfect removal of crystals during AFC. RAFC adds recharge, in other words, magma mixing to it. There's a huge proliferation of models right now, and they're all fine for modeling magmatic processes. Okay? And models are pretty good because they may pretty cogently eliminate some processes that just don't work well with the models. And they may support others. But mathematical models cannot prove that any process actually takes place. Okay? It may work in the model, but the Earth doesn't always listen to those models and often has its own ideas. Sorry, I'm not trying to dismiss models. They're very, very powerful and they're very good for many things, but you always have to interpret them with a certain amount of prudence. Okay? And none of these models, incidentally, has yet managed to produce a granite in any amounts from apparent basalt using reasonable assumptions of conservation of energy, etc. Okay? So how do you do this? I could end here and be early, I think, by saying, well, you just don't get granites, but we see them. So there's two steps toward a solution. One is we realize that the batholiths don't have the shape I showed you earlier, that they just keep getting bigger with depth. This is what the Boulder batholith looks like in central Idaho, based on some pretty good seismic imaging. Of course, this is a solidified batholith now. Okay? Notice they tend to reach a level at which they reach a certain gravitational stability and spread laterally instead of rise, so that maybe we don't have to create quite so much batholith as we thought we did, or so much granite. This is only a tiny step toward the solution, however, because notice all this stuff called gneissic country rock here. I wish I'd quit doing that. That's pretty granitic also. So they're part of the problem, not part of the solution. Okay, so what I've realized, having read for this third edition, is that there's a lot of really interesting advancements going on toward what magma chambers are really like. And that's sort of the second half of my title. First of all, geophysics. Okay, these are problems with the classic idea that have been in our minds for so long, that a magma chamber is a big blob of mostly molten rock. Okay? Geophysics suggests that that is not the case, despite very closely spaced arrays on places where we suspect there should be a granitic magma chamber, like at Yellowstone in the United States. We put great arrays that are capable of detecting anything down to maybe 5 cubic kilometers in size, which would be pretty small for granite body. They don't find anything of that size. Magnetotellurics are a method in which you can determine the electrical conductivity at depth. And that is much better at imaging small percentage melts. And magnetotellurics are now suggesting, seismics say, there's no big melt dominated anything down there. Either this is an unusual time in which all of the magma chambers have already solidified, or they just never really existed in the first place. Magnetotellurics say there's stuff down there that's got a lot of liquid in them, but they are dominated by crystals, not liquid. A term we now call crystal mush. Textural evidence. If you look at rhyolite ignimbrites in particular, because that's a place where you know that liquid came out recently, and that's where you'd expect to see a big magma chamber of granite underneath, again, that we don't, we find that all of those rhyolites have a whole bunch of different crystals that are not necessarily in equilibrium with themselves or with the matrix host. So here's a few terms you might not be familiar with: xenocrysts, anticrysts, and autocrysts. Okay, they're all types of phenocrysts, which is a term I hope you remember. Okay, xenocrysts are phenocrysts that have no place in the ignimbrite that you found them in. Okay, they're the crystalline, single crystal analog of a xenolith. Anticrysts are from a different cycle of, they're related, but they seem to come from an earlier phase of the liquid, not the later phase of the liquid that they're found in now. In other words, you might find an old, let's say, a highly calcic plagioclase crystal in a rhyolite ignimbrite where the rest of the crystals are all pretty albitic instead. But there's some correlations between these, that they look like that plagioclase crystal was part of a melt that evolved to this one. And autocrysts are what we really thought of as phenocrysts, and they belong there. Okay, so phenocryst is a great term in general, but if you're really trying to stress that they belong there, you would call those phenocrysts autocrysts, and then you might be comparing them to the others. Okay? All of these things are in these rhyolite ignimbrites. Also, there's multi-generational zircons that you find in these ignimbrites, saying that they've been through more than one melt or melt solid mill. Some of the anticrysts are zoned, and melt inclusions are becoming increasingly popular. These are inclusions held inside crystals, and they become armored from reacting with later melts. So you end up with a huge variety of melts that were existing at one time and are now trapped in plagioclase crystals, olivine crystals, and you're suddenly saying, wow, all of these different melts, where do they come from? Why are they here? So it looks like, and again, rhyolite ignimbrites are the best because they're just delivering all of this stuff at once. Granites have a lot more time as they cool more slowly to sort of cure and anneal a lot of this evidence out. So, what can we say from this? Largely liquid magma chambers rarely, if ever, exist. And there have been multiple magmas with included phenocrysts that differ from one magma to the next. And magma mixing seems to be ubiquitous. That is how we find so many of these xenocrysts, anticrysts, melt inclusions all together. So far, my talk has been kind of vanilla, but I think it was Microsoft suggested that I put something a little more dramatic for this sort of transition into a new way of looking at magmas. So here's a big splotch for you. Transcrustal magma systems is one of the terms applied to these. Okay? Magma chambers is an evolving term now. What we used to mean as magma chambers in the classical sense are rare. What we can now consider magma chambers to be these mush-dominated ones with scattered melt-dominated lenses within them. And let me show you an illustration. This is one of the diagrams that will be in my third edition. Incidentally, I'm hoping to have an E edition in which it'll be in color, so some of these things I've done in color here first. Okay, so here is the entire crust. Here's the mantle down in purple, the crust ranging from a somewhat more mafic and refractory lower crust to a more evolved upper crust. This will be the stuff, again, that Professor Rollinson will be talking about. And here come some of these first basaltic melts, these magmas created by partial melting of our mantle. They're going to rise because they are buoyant, but when they hit the base of the crust, their buoyancy is greatly reduced because this crust is less dense in the mantle. That's why it's up on top. And these will tend to pond. So notice here's our first bit of magma mixing. More and more of these things tend to add to this large accumulating liquid at the base of the crust. And you might notice I've drawn in a little bit of melting and assimilation here. Some people have called this the MASH process, melting, assimilation, storage, and homogenization. And so by a combination of crystal settling and assimilation, etc., you get a more evolved upper portion here, and some of these can be tapped off. So notice now that these rising melts are more evolved than these ones down here. So these feed into a magma reservoir, you might call this, or you might call this a magma chamber. And this would be a melt pocket, or more like the classic sense of a magma chamber. So these things keep adding. Again, magma mixing. This is entirely solid. This is progressively more and higher percentage of liquid until finally you get in something that is predominantly liquid anyway, 50, 60, 70% melt. Okay, so notice that on the walls here you get assimilation in from the crust. Here you crystallize onto the walls. Liquid migrates out of the mush to form some of these pockets of more evolved liquid. And then from these, you end up sending up escaping more buoyant melts into a yet higher magma reservoir. And the same things happen here of assimilation, crystallization, evolution, and you come up with something yet more evolved. And notice I tried to show a caught in the act here of a replenishment event of some of this melt going into this melt pocket, which overpressures this pocket and releases a caldera supereruption of rhyolite. Here's an escape that might make a smaller eruption instead. So my illustration shows two of these transcrustal magma, or two of these magma reservoirs in a transcrustal magma system. Here's a little inset that shows that maybe you have 4 of them, maybe you have 5 of them. What makes any one of these stable is a matter of heat balance. If you put in enough magma into this, compared to the heat that's lost onto the walls, you'll stabilize one of these things. As soon as you get less magma input and more cooling, which happens further up, these will be more ephemeral and could eventually completely crystallize, and another one might form somewhere else. The idea here, though, is that you're really looking at something that might be akin to a distillation column of multiple levels. Each level going up creates more evolved and more evolved and more evolved magmas. It's not very hard on the back of an envelope to start calculating how each one of these becomes more and more evolved to the point where, back down, more and more evolved to where this could well become a granitic body that we see right in here, or even a granitic body here. And most granites, when you get out in the field, are not homogeneous anyway. They go from pure granites to tonalites, even diorites, and things like that. So although I never quite answered this question in editions 1 and 2 about how you can produce granites during processes of magmatic diversification, I think we finally cracked this problem by edition number 3 by these transcrustal magma systems. And I think this is pretty interesting stuff. I thought I'd share that with you because that's been one of the more fun findings as I've been working through my revisions. I don't know what the timing is, but I'm hoping I stayed close to a half hour. And I'm open to questions. Thank you.
Thank you so much for such an enlightening and informative talk, sir. So should we carry on to the question answer session?
Sure.
Okay. So,
I don't guarantee the right answer, but yeah, I'll give it a shot.
Okay, sir. So, sir, our first question is regarding pyroclastic volcano. Are they related genetically to any tectonics or geological settings?
Yes and no. A more complex question than would apparently seem from the beginning. Yes. The more we tend to associate pyroclastics with more silicic volcanics, which are going to be arc related. And of course, continental arcs are even more so than island arcs. So that's why you tend to see these caldera super eruptions in places where subduction is taking place beneath the continent. And by the way, that's yet one more method I haven't mentioned about creating granites, and that is through the subduction mill, which is a completely other story, but very helpful in making the granites too. But those are more silicic melts, and therefore they tend to hold the volatiles that are dissolved in them, and once they reach a stage of combined crystallization and depressurization as they rise, they can eventually trigger explosive eruption. Having said that, now that I live in Hawaii, it turned out that using a lot of the more recent uranium series dating techniques, we're finding that there's a lot of pyroclastics within the Hawaiian lava flows. The Hawaiian lava flows by volume are vastly predominant because they come out in such copious amounts during an eruption. But if you were to look at the timing over at least the last few thousand years, the Kilauea eruptions have spent more time with ash and pyroclastics than they have with lava flows, even though we tend to see the lava flows more. So I'm just adding a little caveat there that pyroclastic flows can happen anywhere where there's volatiles in magmas, and as a result, when those volatiles are released, you're going to get some activity. And of course, some of this here in Hawaii is also groundwater activity, makes pyroclastics too. So, again, simple reiteration, yes, you'll find more pyroclastics at continental arcs and subduction zones than you will at mid-ocean ridges and the ocean islands, but you can find pyroclastic material in almost any volcanic region.
Okay, thank you so much, sir. So the second question is, in an igneous terrain with multiple rock types, we get geochemical compositional variations in the host rock from place to place. So we propose it might be multiple magma influxes, but ultimately we need isotopic ages for support. What if a single age is preserved in all those rocks? Is it possible that there might be any physical process where white compositionally variable rocks can be formed from a single magma chamber?
That is another question that gets, you can go completely over the deep end on this. First of all, let me mention that it's not the isotope ages that are going to be as important as the isotopic ratios that show you a fingerprint of different sources. It's the initial ratio of strontium 8786, much more than the age you can derive from the decays that are going to lead to heterogeneity. Can you remind me, did the question ask whether you can get different sources for within a single magma chamber? Was that what part of the question was?
It was like there might be any physical process where white compositionally variable rock can be formed. Like, is it possible?
Sure. Absolutely, and you can see it right here in this diagram too. There is a compositional range from this more primitive or mafic rock here, gradually getting more and more evolved here. And if you were to tap off from over here, you'd get this kind of a volcanic. If you were to tap off from right here, you'd get this kind of a volcanic. And again, if you got into here, you'd even get this more rhyolitic volcanic. So yeah, all of these magma chambers are diversifying. What I haven't touched on here is how heterogeneous the mantle is. And that's another question that would take more than another half hour to answer. But there are definitely areas in the mantle that are, well, let's say recycled oceanic crust that came along in the subduction zone. So there would be bits and pieces of that in here. Some of those would be melting. So all of these things need not be exactly the same. They'll probably all be generally basaltic, but they certainly have a different isotopic signature that was an indicator of their source composition. You wouldn't be able to detect that using the major and the trace elements very easily, but the isotopes would be flying the little flag of heterogeneity. So if I understand the question correctly, you can produce compositional differences, variation from a single magma chamber, but the isotopic heterogeneity would be a source characteristic and would depend more on the inputs to the magma chamber as well.
Okay, thank you, sir. Sir, there is another question. That is, suppose we want to model or visualize the geographical extent of the original magma chamber. Can you share your approach about like how to begin such work?
If you wanted to model, say again, please, if you wanted to model the
geographical extent of the original magma chamber.
Okay, so let me see how I'm interpreting that. If you're looking at the geographic extent of the origin, that would mean where did all of this stuff come from and how did it focus on here? This is a big question for mid-ocean ridges, for example, because all of the volcanism gets very close to the very axis. But the part of the mantle that's being melted is much, much broader, and those melts are being focused into that axial region. So if that's the question, modeling the width of those zones and the way that the melt is focused the answer is going to go beyond what I can make sense for you of right away. But the literature on mid-ocean ridges is rife with those models. And of course, they're not all the same. If on the other hand, you're looking at trying to just model creating a magma, and for making into a magma chamber, there's all kinds of fairly simplistic models from batch melting to fractional melting to do that. Okay? So I'm not quite sure about the question of whether you're talking about geographically how it's contributing to the magma chamber or geochemically whether you can model creating a melt and filling a magma chamber. Both type models are available, and a lot more models too.
So there has been a question that popped up in the chat. It says 50 to 60% partial melting seems too high. Is there any geophysical model to support this?
I'm sorry, 50 to 60% of what?
Partial melting.
Oh, partial melting.
Yes.
Yeah, no, I'm not saying 50 to 60% partial melting. If they're talking about this 50 to 60%, that is the residual melt after crystallization. It is not the partial melt. Nowhere am I advocating trying to melt something 50 to 60%. The melt will escape. Oops, sorry. The melt will escape. Slideshow. Slide. The melt will escape from the source down in the less than 5%, and certainly by 10%. 50 to 60% melting is, as your questioner appropriately points out, is out of the question, I guess. It would be as good as anything. That's not my intention when that 50 to 60% melt. That's residual melt.
Thank you so much, sir, for clearing that up.
Yep.
So, we have another question, which is that mineral formation in a rock depends on the effective bulk of the host rock. So, whatever pellitic rock might have melted, might have reached a certain grade of metamorphism, like granulite, but due to certain characteristics, the bulk doesn't host a pyroxene. So, what should be the nomenclature for such a rock?
Okay, so you're talking about a high-grade metamorphic rock of a pellitic sediment, if I understood. And,
Yes.
And did they say the pyroxene was stable?
No, sir. They just say that the characteristic bulk doesn't host a pyroxene.
Oh, yeah. Well, that certainly happens quite a bit. And you can also there's the whole pyroxene paradox that comes up with mantle melts too. Is it a matter of just? I still don't quite understand the question. Is it a matter of what would you name such a rock, or how would you explain the fact that it doesn't have a stable pyroxene in it?
So just what should be the nomenclature? Like probably with the minerals like garnet, biotite, aluminosilicates, platinum.
Well, the nomenclature, again, if I understand the question correctly, the nomenclature for naming rocks, particularly, thank God, metamorphic rocks, are pretty darn simple. They're based on the mineralogy. But of course, everybody wants to propose some special rock. Since you're in India, the name Charnakite comes to mind. A lot of people would like to use that term as a fairly general term. Other people would like to restrict it to the rock, the only rock that makes up Job Charnak's tomb, and nothing beyond that. It's a pyroxene granulite. And in this case, I believe the question is talking about a granulite facies rock that has no pyroxene in it. And how would you recognize it as granulite facies? Well, there are ways to do that, but the more silicic rock, I mean, if you take a quartzite and metamorphose it to granulite facies, there'll be no indicator whatsoever that it's granulite facies, and you have to use the other rocks around it to be able to come up with characterization of the facies. If this is a peelite and it's been metamorphosed, you'll tend to, at granulite facies, you'll tend to run out of hydrous phases pretty quickly. But you do not necessarily have to produce pyroxene, I suppose. I think that's my concept of what the question is. If I misunderstood, I apologize.
No, it's completely fine, sir. Thank you for your insight. So we have the fifth question, sir, that conventionally we use iron and magnesium based thermometers and some iron, magnesium and calcium based barometers to predict the grade of metamorphism. So, or should we use characteristic mineral assemblage for such? So, however, nowadays the pseudosection modeling in metamorphism has reached up to MNNC, FK, MASH, TIO systems. So, what's the acceptance of only iron and magnesium based thermometers in metamorphic work nowadays? Like, what is your take on this?
Yeah. Well, I cut my teeth applying the kind of standard geothermometers and geobarometers. In fact, I worked on a little program that would take all of my data out of my spreadsheet and crunch out any number of geothermometer estimates. And it's pretty easy. It was pretty straightforward, and it works relatively well. But I sense appropriately, I think, that today they're definitely going to use some of the more integrated thermodynamic programs in the KFMASH, name it, add what you need. And I think I gave a sense of that in my chapter on geothermometry, that these runs using the software, you can contour it for the compositions as well. So you can actually use a fairly robust method to come down with a pretty accurate temperature and pressure estimate on that. If I were doing research on it today, I'd employ both. But I definitely sense that the trend is going toward using the modeling software.
Okay. Thank you so much, sir. So we have a last question. So as you know, you are very popular among the young minds of geological community in India, and I'm sure all over the world as well. So some of our audience audience are curious to know what attracted you towards geology when you were a student and motivated you to pursue research in the subject.
Well, I don't know how things are in India, but rarely do students graduate from our high schools dying to be a geologist. They may have had one, what we call earth science course in their high school curriculum, but there was an elective not required, or they may have a little module here and there. But usually they want to be a biologist or a chemist or an engineer or a historian or something like that. For me, I wanted to be a chemist. So I remember it was my second year in chemistry, and I was in my quant lab where I'm titrating yet one more time. And I was looking out the window and watching these students in the next building across the way loading into their vans from the geology department and going on a field trip. And I said, I want to be like them. And I found that when we were teaching at Whitman College, the same thing sort of happened, that we get people because they took our intro course and realized that they could do science and be outside. Biology used to be more like that, but they've gone pretty molecular. So you're not out there catching fish or categorizing toads so much as you're working with molecular biology. So at least at Whitman College, the geology department just caught all the kids who wanted to go outdoors and be a scientist. And that's usually a pretty good crowd, in my opinion. So, and then I thought back, and that kind of happened to me too. I really admired those people, my fans who said I got stuck in this lab where I am. There are true confessions.
Thank you so much, sir. We have more questions? Okay. So we have more questions coming in. Okay. So is it okay if we ask more questions?
Sure.
Yeah, okay. Sir, is it possible to differentiate a granite formed by fractionation that formed by low degree of partial melting of a felsic protolith?
Yes, that's the whole idea, at least usually, or often enough. Let me back up. That's what I-type granites are versus S-type granites. I-type are igneous type, and S-type are sedimentary type. And usually, just in generalizations, usually the S-types have more muscovite or aluminum silicates in them. They're much more aluminum rich, whereas the I-types are what you might expect if you were to model along the lines that I'm showing here. They're going to be more calcic and a little less sodic, a little less potassium, and a little less aluminum. So yeah, there are ways, but most of them are based on sort of the more common categorization methods we've looked at. There's also a whole slew of trace element methodologies. You'd have to dig around in my chapter 18. I'm only revising up through 13 right now, so the material isn't quite as fresh for me, but there's a lot of ones based on trace elements and trace element ratios and a lot of triangular plots that you'll see that are designed to distinguish rock types into their tectonic igneous associations, like arc-related or melts of sediments, etc., because although it's very easy to go and to an area like I'm showing here on the diagram in, say, California, where some of these ignimbrites, or Nevada, where they're happening in the U.S., and say, well, gee, we're right, this is the arc, well, of course. But a lot of older rocks are dissociated from that, so we don't quite have the ability to make the correlations. And the older they get, the more tenuous that is. So a lot of people have been looking for ways based on major element chemistry, trace element chemistry, and even some isotope chemistry. So yeah, the answer is yes, you can.
A question.
Okay. Okay. Thank you so much, sir. So I'm delighted to inform you that more than 400 participants joined the talk. They,
Wow.
yes, sir. We had more than 400 views.
How many years of teaching would be to reach that many back at Whitman College? Yeah.
Yes, sir. Thank you so much for inspiring us. And sir, now I would like Professor Prabhakar Naraga to conclude the session.
All right. Well, thank you, everybody. It's been fun.
Yeah, Professor Winter, thank you for your wonderful lecture on the magma chambers. And as you can see from the number of views, and all of our students and faculty members are excited to listen your lecture. And I must thank you for making this opportunity to available for us and presenting this lecture. And yeah,
You're quite welcome.
yeah, thank you very much.
Yes. I had fun. Thank you.
Yeah.
Good luck, everybody. May COVID smile on you this coming year.
Okay. Thank you so much, sir. We had more questions, but due to constraint of time, we could not ask you everything.
Yeah. And well, with 400 people, I guess we could be here all night, huh? Yeah.
Yes, sir. Thank you so much, sir.
You bet. But again, shameless plug, actually. Keep an eye open. There'll be a new edition coming out, and hopefully it'll be a color e-edition. But if my rate of progress on revising is as slow as it has been, don't expect to see it until the end of next year.
Yes, sir. Definitely. We'll look forward to it.
All right.
Thank you.
As I say in Hawaii, aloha.
Thank you, sir.
Thank you.